So today we have Brittany's story speaking on molecular configurations and persistence, branched alkanes and additive energies.
Awesome. Thank you so much, Sarah, and to anyone else who's been organizing GROOT and doing all this cool stuff for us. So as Sarah mentioned, today we'll be looking at molecular configurations and persistence, and specifically we're going to focus on a type of molecule called a branched alkane. So just a quick outline so we don't get lost in the trees of where we're going. First, we'll talk about energy landscapes and what those are, because I had to learn myself when I started this project. Then we'll do a little refresher on some persistent homology and Morse theory to give us the ground of what we're going to actually focus on today. We'll look at what a branched alkane is and what that looks like in this structure and organization that we have. And then we can finally talk about these energy landscapes of branched alkanes. Look a little bit at future work, what I plan to do this year with some of my collaborators as well as independently. And then of course, acknowledgements, because we always got to have those. Okay, so to start off, what is an energy landscape? So we're going to be looking at strings of carbons and trees of carbons. So if you have a bunch of carbons, like we have right here, so this right here is a carbon molecule, right? And carbons attach to each other. They like attaching to each other because of how many electrons they have in their outer shell. And so we have a chain of 4 carbons. And you can imagine that if we rotate around this bond right here, right, I can get from the configuration that I have on the left, which I think starts like this, to the configuration I have on the right, just by rotating along that bond. Okay, so each place in my rotation is going to correspond to a certain energy value that the molecule gives off. So if we have the configuration on the left-hand side, this is actually going to be a minimum energy value because these 2 pinky carbons are farther away from each other. Whereas this energy configuration on the right, at least on my screen, the boat one, is going to have a higher energy value because these 2 carbons are as close together as they possibly can get over that entire rotation. So what we're inputting is we're inputting angle value. So we create a starting angle, go all the way around, and that is going to give us a domain of the circle. And so with this, chemists can figure out what the energy function is supposed to be. So down here at the very bottom, this is going to be our energy function. And as you can imagine, this energy function is going to change based on what our molecule looks like, right? If we add more carbons in, it's probably going to get more complicated. And if the carbons are doing more like tree-like structures, it's also going to get a little different. But basically what this energy function is it's just going to be a sum of cosines, which is kind of nice because mathematicians like cosines. They behave in a very predictable way, and they give us something to kind of work with that's nice, at least to start with. Okay, so in this graph we have below, right here, that's just going to be a plot of all of the energy values over that rotational change of our molecule. OPLSUA is just one specific type of energy landscape. It's probably arguably the most simple type, and so that's where we're going to start as far as all of this math is concerned. Okay, so we're mathematicians, right? We don't just want to do chemistry. So let's talk a little bit about persistent homology. So our overall goal of the project is to calculate the sublevel set persistent homology of branched alkane energy landscapes. Okay, so alkane is just going to mean chain of carbons. And you're kind of stuck with the hydrogens too, but we don't really worry about them. They're not really important in the OPLSUA case. Once we actually make a more complicated model, then they'll come into play. But for now, we're just going to focus on carbon. Branched just means any tree. So for any tree of carbons, we want to figure out the sublevel set persistent homology of that energy function that we looked at on the last slide. Okay, so here's a different molecule. Now my bond is going to be orange. And as you can see, whereas before we only had a single chain of carbons, now we have a little fork at the end. So if we were to plot out the energy landscape like we have below, this is what it's going to look like. So it looks a little different than the one on the last slide. And I know this picture is a little busy. We'll have a less busy one later. But we want to figure out what the sublevel set persistence is of this energy landscape. So if I take my bar, if I have a horizontal bar and I slide it up along my graph, the amount of components I have are going to change based on where I am. So if I start at this line, this purple line at the bottom, which is going to correspond to energy value alpha, right? I can see that I have 2 points that are suddenly born at this alpha birth time. So if I keep traveling along that line, as soon as I hit this blue line beta, right, I'm going to hit another point. So I'm going to introduce another bar. So the number of bars is just corresponding to the number of birth times of certain features. And then as they die, that will be when these certain features die. So if we take our horizontal bar and we keep traveling up our graph, then eventually we're actually going to hit a point, this maximum value gamma, which is in this pinkish reddish color. We're going to hit gamma, and what's going to happen is those two minimum values are going to merge, and it's going to kill one of them. So the way we denote that in our persistent homology diagram is we say, okay, this is going to be the death of this bar. So we have a bar that dies at gamma. So if we keep traveling along, eventually we hit this delta line where finally we have our entire graph encompassed in our picture. And since this is actually over the circle domain-wise, right, we can picture that these 2 points that are at beta are actually looped together. It's just easier to visualize flat. So when we hit this delta value, then what happens is that we're left with one component and we're left with one circle. So this blue bar down here denotes the birth of a circle, at least in this context. Or a one-dimensional hole, if we want to be a little more proper. So before we move on, does anyone have any questions on this slide?
On the left-hand side, is the energy function again corresponding to like rotating the angle of one of the carbons?
That is an excellent question. And yes, so specifically for our case, the energy functions we're always going to worry about are going to be these rotation functions. Now in chemistry, that's not the only thing that we could have as an input. We could have the bond length. So like if this is a really long bond, then these carbons are far away and that'll change the energy values. Or if it's really short, right, they're going to hit each other a lot more. But specifically for the purpose of this talk, we'll be focusing just on those rotational values.
Thanks.
Of course. Awesome. Okay, we'll keep cracking. If you have questions, feel free to let me know. So the persistent homology is great and all, but we'd like a way to kind of simplify all of this information that we just gathered. So we're going to do a little bit of more theory here on the side. So we have the same energy function that we had before, this isopentane or that branched carbon we had on the last slide. And what we're going to do is we're going to denote what happens, but we're going to do it in a slightly simpler way. So we talked about how as we slide this horizontal bar, we have things that are born and things that die. So in this case, let's start again at the bottom and see what happens. So as soon as we hit value alpha, which is right here, then we have 2 points that are born, A1 and A2. So those can be seen right here. As we keep traveling up this bar, what's going to happen is as soon as I hit that beta value, I get another point that's introduced. Now on here, it looks like I have 2 points, but just remember that we're looking over the domain of the circle, so these points are actually associated to each other. So at time beta, we have this B value that's born. Okay, so we keep traveling up, and eventually when we hit C, this critical point C, well, that's going to correspond to this line that connects those two A1 and A2 points. So now as we had 3 components before, we now have 2 components because 2 of them merge to form 1. And we can keep playing the same game until finally we merge into one component that forms a one-dimensional whole. For some reason that sounded weird in my brain. Okay, so the reason we have to have this Morse theory is it's going to play in nicely with what we actually want to conclude about these energy landscapes. So there's a well-known lemma in Morse theory, I definitely did not come up with it, that connects Morse theory to sublevel set persistence. So if we have a Morse function, which is just a nice function that's going to play super well with everything that we have, then the birth and non-infinite death times in the sublevel set persistent homology correspond precisely to the critical points of F, which is kind of what we saw in the last slide, right? We had all of these things change as soon as we hit these minimums or these maximums of our energy function. And further, we're going to be able to say that each k-dimensional bar has birth time corresponding to a critical point of index k, and the death time either equal to infinity, so if we have an infinite length, semi-infinite length bar, or it'll correspond to a critical point of index k plus 1. So in the previous slide, right, our minimums have index 0, so we have those are being born. In those index 0 critical points, when we hit an index 1 critical point, that was when those components were kind of killed off or merged, so to speak. So furthermore, the number of semi-infinite bars in dimension k is given by the k-dimensional homology of M. So if we know specifically what our domain of our function is, I'll be able to tell you all of the semi-infinite bars, right? So for example, on these, we have a circle, right? We might have a couple ups and downs along the way, but because our domain is over a circle, I can tell you that we're going to have one semi-infinite 0-dimensional bar and one semi-infinite 1-dimensional bar, which indeed, if we go back a couple slides, that's exactly what we had. Whew, okay, so that's some of the background. Some of you may be super familiar with it. This is like second nature. Some of you might be a little less so, but at least now we kind of have common ground of which to speak. So how are we going to kind of connect this all back together? So as you can imagine in chemistry, right, we're going to have a lot longer molecules than the ones I had on the previous slides. We're going to have things that like can combine together, and we could technically have any tree size of carbons that we wanted. So we have to have a way to kind of take what we know and combine it somehow. So that's where additive functions on a product space are going to come in. So if G sub I is a function from X sub I to R, is a collection of functions for any number of I, then one can define their sum on the product space in the following way. So I think this is a little easier to explain with a picture than it is to actually explain in words. So here are the two molecules we've already experienced. My molecule with 4 carbons, my molecule with 5 carbons that forms like a little fork. So I want to take these chains of carbons and I want to smush them together. Seems like a reasonable thing to do. So if I have my function G1, which talks about the energy function for this 1,2,2,1 bond, and I have this function G2, which talks about this energy function for my 1,3,2,1 bond. And just a quick note, the numbers inside are just the degrees of the vertices. Then if I combine them, it would be super, super nice if I could just add them together, which is exactly what I get to do, right? Because the way I can think about it is that if I have this molecule, if I rotate along the 2,2 bond, that's not changing anything along my 3,2 bond. Whereas same vice versa, if I rotate along my 3,2 bond, that's not changing anything on my 2,2 bond. So our actual function, so if I give you a position of where my 2 bonds are, I'm going to get an energy value output. So that is indeed going to be an additive function on a product space because I have no weird merging of variables going on. Yeah, that was a lot of chemistry. Does anyone have any questions?
I do. Can you visualize that addition as kind of like literally taking one of the bonds or one of the trees and sticking them together, kind of like vector addition almost?
Yeah, that's a super good way to think about it, right? Because you have to be a little careful, and I'll go into the explicits of why we have to be careful. But yeah, we're just basically saying, okay, if I have this 2,2 bond, which I have denoted in red, right? That one's getting put in right here. And then down here, I'm taking that 3,2 bond, and shoving it in right here. So thinking about it in terms of vector addition is kind of a good way to visualize.
I'm curious as to where the ones have gone, because I see the 1, 1, 3, 2, and then I don't see one of the ones and the other one of the ones. Am I making sense?
You're 100% making sense. And that's an excellent lead into my next slide. It's like
Okay,
you planned it. Okay, well, maybe not quite next slide, but I promise you I will come back to your question.
Great.
Okay, so we have these additive functions, and is it Naya?
Yeah, it is.
Cool. As Naya pointed out, right, we have a couple things we're gonna, oh, it's so good to see faces. We have a couple things we're gonna have to address, right? Because it's not gonna be quite squishing them together, but we'll be able to get around that a little bit here in a moment. But the reason we want these additive energy functions is specifically because we want to use something called the persistent Kunis formula. So the Kunis formula is something that's been around for a hot minute. I found it in Hatcher when I was like first doing research for this project. And my academic older brother, Joshua Mirth, worked on this project before me and figured out that this persistent Kunis formula found in this paper by Perea and his co-author, whose name I can't remember right now, is actually going to apply to this situation. So what this persistent Kunis formula says that if I have a natural short exact sequence of graded modules, which our energy functions are going to fall into, then what I can say is that I get this short exact sequence, and if h sub I of x and h sub j of y are pointwise finite, then this BCD, which just means barcode, of if I take the two modules and I cross them together, then I will be able to give you the birth and the death time of each barcode. So down here, closer to the bottom, this right here is going to correspond to the birth of a bar, whereas this will correspond to the death. We're also going to have something kind of weird happen, which we'll talk about later on when we have something to look at. But this is also going to give us bars. And this part comes from this torsion part that we see in the short exact sequence. So what this persistent Kunis formula is saying is it's saying that I can think about my persistent homology for these larger molecules as sums of my persistent homology for my smaller molecules. So I get this kind of additive piecewise structure that we want in order to be able to say something about larger molecules that we might not have as much information for. Okay, so here's where we're finally going to get back to your question. So just to remind us of our goal, we want to calculate the sublevel set persistent homology of branched alkane energy landscapes. So what Naya brought up before is that technically, when we were looking at the energy landscape, we had V1, 2, 2, 1, which corresponded to our molecule that looks something like this, where this bond in the middle is the one that's super contributing, right? Because if we rotate around here, it's not actually going to change anything. It's only when we rotate around this center bond. Now, we can't quite glue it, so to speak, because we have this extra one on the end. So what we're going to start with is an approximation. We're going to say, if I know my energy landscape for this 1, 2, 2, 1 bond, anytime I see a 2, 2 as the middle bond, I'm just going to treat it as a 1, 2, 2, 1. Technically, what I should do is I should treat this as a V1, 2, 2, 3 bond, right? Because this degree of this like outer carbon actually matters, right? Because if it's a super high degree, that means there's a bunch of other stuff going on here, and that's going to impact the energy function. But for a starting point, we're going to approximate with 1, 2, 2, 1. Okay, so we'll do the same thing for this 2, 2, 3, 1, which we have right here. And we'll approximate that with 1, 3, 2, 1. If we were to not approximate, carbon can go up to degree 4 of connections shooting off of it. And so what that would mean is that we have 78 different possible energy landscapes to consider. And chemists actually, we have not at least been able to find all 78 of them, right? Because calculating this stuff takes time, it takes computer power, and they don't necessarily need it all the time. So they basically, like, is an as needed thing, they calculate these energy values, except for these really small ones, because these are pretty straightforward to calculate. So what we're going to do is we're going to use this additive property that we talked about earlier. So if I want to calculate the sublevel set persistent homology of this energy landscape can be given by this function that I'm going to box right here. So phi1 is going to correspond to my 2,2 bond. Phi2 is going to correspond to the position of my 3,2 bond. And then the only other weird thing that kind of happens is because of this 3,2 bond having this branching thing, we have a couple other pieces that we need to include in our energy value function. So I got this from a few chemists that we're working with, Dr. Aurora Clark from Washington State, and Biswajit Sadhu, one of her students, has been working with us on this project. And so he's been super helpful of introducing me to all this chemistry and explaining where it comes from. So we need to think about, since I technically have two branches that are coming off, that means I'm going to have two terms for my phi2 value. I'm going to have the one that goes positive theta and the one that goes negative theta, where theta is just this angle bisector between our two leaf carbons, or carbons with degree 1. So as we can see, if we actually break down what each of these functions are, we're just going to get a sum of cosine functions, which most of our computers can handle fairly well. So we have some stuff to work with at this point. So if we're thinking about just these inner degrees of our carbons, and we're going to just approximate our energy landscapes by saying all of our outer carbons are going to be 1s, then I have 6 possible bonds that can appear in my branched alkane. Their fancy science name is on the right. The way I'm going to denote them is on the left. I think it's easier to think about them as 1, 3, 2, 1 than it is to remember tetramethylbutane and remember what that means. But that's just my personal opinion. So for each of these base bonds, we're going to have a corresponding energy landscape over the circle, right? Because they all have this rotational thing that's changing the energy value of our molecule. So we'll look at the first 3. So 1, 2, 2, 1, 1, 3, 2, 1, and 1, 3, 3, 1. So if we look closely, and I've stared at this long enough that I can point out a few things, these two are very similar, right? They have the same shape, same number of critical points, mins and maxes, and they have the same bar structure, which all of these are connected, of course. But it's kind of easier to visualize when it's written out. So the 1331 and the 1221 might not look exactly the same right now, but that's just because they were initialized at a different point. If I was to take the 1331 and shift it just, let's see, what is this, 60 degrees, then we would have the exact same picture that we have on the left. This one, isopentane, let's go with green, is our problem child. It likes to be different than everyone else, which is great, except when you're trying to calculate numbers of things. So this one has a little bit of a different structure, right? Because this is actually going to have 2 absolute minimums, whereas the other ones only have 1. It's only going to have 1 local min, 1 local max, whereas the other ones are going to have 2. So it'll look a little bit different. And I see there's a chat. What are the dashed and dotted lines? Ah, that's such a good question. So if I go back to the previous slide, remember how we had this sum of energy functions over here where I said, okay, it matters that we have this leaf carbon and we have this plus theta minus theta. So if I go back down, if I look at my energy landscape for isopentane, I have my function for plus theta, which is going to be one of the dotted lines, and my function for minus theta, which will be the other one. The orange function is going to be what happens when I sum those both together. So that was an excellent question. And then as you can imagine, the more leaves we have, the more functions we're going to have to add together. So if we go all the way up to our carbons that have degree 4, we're going to get a bunch of these dotted lines. We get a little bit of numerical error for the 1441 just because there's some weird summing chemistry stuff that has to happen, so it doesn't look quite as symmetric as it's supposed to, but that's a work in progress. So on this page, we can see that these all look the same, which is originally was kind of weird for me, right? All of our pictures look the same. We have 3 absolute mins, 3 absolute maxes. Our bar structures look the same. But if we think about this in terms of our rotating carbon, we now have this carbon that basically the points form the points of an equidistant tetrahedron. So as I rotate that around, I get that rotational symmetry every, whatever 360 divided by 3 is, every 120 degrees. So it makes sense that all of these are going to look super similar. So all of these have 3 absolute mins and 3 absolute maxes. Okay, any questions so far? Okay, we'll keep moving. So now we have all of the tools. So we can finally start talking about how we're going to take these energy landscapes and combine them. So we'll start with one of the more straightforward branched alkanes. We'll say, okay, if I have a 2,2 and a 3,2 and I want to add them together, then let's see what happens. So I went ahead and labeled all of my bars. So let's explain what this is a little bit. So this right here is going to correspond to my 2,2 bond, whereas the other one will correspond to my 3,2 bond. And these are just the persistence diagrams from our previous slides, right? So what I want to do is I want to say, okay, if I know my persistence diagram for 2,2 and I know my persistence diagram for 3,2, how can I squish them together? So sure enough, it's going to look a lot like you would expect for the most part. So I have labeled all of these bars, which is kind of hard to see. So we'll zoom in a little bit. So this top bar is what I get when I take I1 and I add it to J1. And sure enough, we had those alpha, beta, gamma, delta values. So this is alpha 1 plus alpha 2 is when this bar is born. So it's born when my I1 bar is born plus when my I1J bar is born. And that pattern is going to continue for all of these, mostly. Because if you've done any combinatorics, you know that if I have 4 things and I can add them to 4 other things, however many ways I want, then I should have 16 bars. But I don't, I have 20. So initially, I was very surprised. And then I went through and actually figured out what was going on. So if you remember that Kuhn formula, I had 2 different lines of text. I said, okay, here's the birth time and the death time of my bars, which depends on the birth and death time of my 2 component bars. But I also pointed to the line below and I said, we're going to have something weird happen that's going to come from torsion. So I have these torsion bars labeled with these dots. And what that means is that if I have the right circumstances, so for example, if I have a bunch of points like this, and maybe a bunch of points like this, and they're connected maybe there, if I increase the height at just the right time, when these things merge, they merge to form a loop. So that's giving me this additional component or this additional bar that I wasn't going to have just by combining my bars together to get my birth and death time. So that's kind of intuitively, at least, with a little bit of a stretched mathematical portion. But that's where these extra bars are coming from. I have this, because I have these circles and everything is super symmetric depending on where we are, we're going to end up getting these torsion bars as we look at different molecules. Any questions?
Is this also partly because you're using smaller things to approximate the entire? Or does that not
Exactly.
matter? Okay.
Yeah, because so if you look at a different type of energy landscape, so there's one called OPLSAA. So instead of united atom, UA, it's all atoms. So it takes into account those hydrogens. You get a lot more noise. You get a lot of other, like, maybe they don't merge at exactly the same point, but because we're approximating, we're getting those minimums and maximums being at the same point. So that's a good way to think about it as well.
Okay. Yeah, that's interesting.
Yeah, and it just shows how really complicated chemistry is. Makes me very glad I'm a mathematician. Okay, so we did it with one molecule. Let's just see what happens if we do it with another one. That way we can hopefully come up with some compare, contrast, and all that good stuff. So we'll look at one that's kind of the same, but kind of different, right? I still have this 2-2 bond, but now instead of having a 3-2 bond, I replaced it with a 4-2 bond. So same as before, I have the 2-2 corresponds to my 2-2 diagram, and my 2-4 corresponds to my 4-2 diagram. So we'll do the same thing we did last time. We'll combine our two diagrams together, and we'll notice some things pretty much right off the bat. This one is a lot more consistent, at least per bar, than my last one was, which is kind of nice. I have all of these bars that are born at the same time and that die at the same time, both in zero-dimensional homology. So red, zero-dimensional homology. Blue, is one-dimensional. And last but not least, green is two-dim. Okay, so it might look a little smoother, but there's a few other things we need to notice as well. If I was to go ahead and count all of these, what I would end up with is 1, 2, 3, 5, 6, 7, 8, 9. 9 bars here, 1 bar here, and 10 bars here. Which I know where we're going, right? So I know what I should have been paying attention to on the last slide, but that's the exact same thing that we had on our previous slide. If we go back and look at our other diagram, too far, right? I actually had the same thing that I had before, which is kind of crazy. Yeah, my birth and death times might be different, but my number of bars is the same. And that is not going to be a coincidence, right? Because we still have these things over the circle, and all of our energy landscapes still have this underlying structure that's behaving very similarly. So we'll actually be able to say something about the number of bars just based on the number of internal bonds, or these colored bonds that I've been using throughout, that we have in our molecule. So the energy landscape for any branched alkane has n choose k semi-infinite bars of dimension k. So the semi-infinite ones are just the ones that go on forever. And this is just an artifact that our domain is S1 to the n. Because it's a well-known fact in persistent homology that if you look at the torus, if your domain is the torus, then we know exactly how many bars it's going to have. So that's the first thing we can say that is pretty already understood, but we can use it then to talk about the number of bars in general. So the energy function of any branched alkane, so F total is just the total energy landscape of the entire molecule, can be decomposed into functions on each bond, x, y, where each function consists of dihedral types. So that's just the numbers 1, 2, 2, whatever. So if Ci is the number of critical points for each bond, then I can tell you exactly how many bars we're going to have. We'll have these 2 to the n semi-infinite bars. That's just the sum over n choose k, right? And that's just however many I got from my domain being the torus. And then the number of finite bars can also be calculated based on the number of critical points of our function, which is pretty slick. And this actually generalizes, right? Because we've been looking specifically at 1, x, y, 1, but I can say it regardless of whether or not we replace these ones with their actual carbon degrees. So specifically, if we're looking at all of the examples we've done previously with this approximation, I can tell you that we're going to have 6 to the n plus 2 to the n total bars, which is kind of nice to be able to say. I can tell you exactly what's going to happen. Further, I can tell you how many bars we're going to have in each dimension. So the sublevel set persistent homology on any analytical branched alkane potential energy landscape has exactly n choose k plus 3 to the n minus 1, n minus 1 choose k. So this is pretty slick, and it comes from the fact that these are still going to be our semi-infinite. Whereas these will be our finite. And just to give you a little intuition of where this proof is coming from, all of our functions that we looked at way back when of our energy landscapes, just all those colorful curves, all of those had a grand total of 6 critical points. They each had 3 minimums of some type and 3 maximums of some type. So when we talked about this Morse theory, like k-dimensional homology is born by k-dimensional critical points, that's kind of where this sum and formula is coming from. So we have some stuff done, but there's still more to do, luckily, because it's going to help me get my PhD. So we are going to generalize and take away this assumption of having one XY1 and replace it with any degree carbons on those outer carbons. We're going to quantify the birth and death times of each bar for the one XY case, one case. So my academic older brother did this for his PhD, but only with strings of carbons. He had no branches. And so my goal is to actually generalize this to be for any branched alkane. And isopentane is still a pain in the butt. That's that 3-2-1. It likes to be a bang. And that's the only thing really keeping me from it right now. So I think as Sarah asked earlier, right, we had these all over a circle or whatever, but we could have those other inputs. So I could have the length of my bond be an input. And so it'd be nice to be able to generalize this outside of just those rotations and be able to include other variables for our molecules. Because as you can imagine, these molecules are messy. They don't behave as well as we would like them to. We'd like to look at other structures. So specifically, you can have these weird things happen where you get things like double bonds. So instead of just having one bond between the carbons, we have 2 bonds. And that's going to change stuff too, because now you no longer have that full rotation that you can do. You can only maybe rotate till about here. And then with enough energy, maybe those bonds actually snap. So there's some other weird stuff that can happen. The other thing we didn't cover is we didn't cover anything with cycles. So if I have a bunch of carbons that form a cycle, this actually changes things. And we're not able to use the same tools that we were before because the domain of the energy landscape of this function is a Klein bottle merged with a sphere with a ring of singularities. So now that it's not a manifold and it's not playing nicely with anyone, it's going to look a little different. The other thing we want to look at and what I'm going to be working on this summer is non-organic compounds. So what happens when we deviate from carbon? Because there are a lot of other different atoms out there. And so it'd be interesting to see what's going to translate nicely and what's not. And that combined with applications to material science is going to be my research for the summer. Okay, so a huge thanks to Colorado State and Delta for supporting this project, as well as NASA. They're the people who are going to fund my research for the summer. And another huge thank you to the organizers of GROOT and to all of y'all for attending. So thank you so much.
Great. On behalf of everyone, I would like to thank Brittany for the talk. Are there any questions for the recording? So I had one question. I was just curious about how much work had been done with things that have cycles in them. You mentioned that's like a whole other branch of tools that you need to use if you consider that. But yeah, I was just curious how much had been done there.
So it depends on the molecule. So the place where it really starts, you have even a little bit of interest is if you have 4 carbons, right? Because you can have, if you think of it like a square, right, you have this position or you have this position, or like, because it's kind of hard to twist. So as you increase the number of carbons, you get a little more twistiness. And the place where it becomes interesting is when you hit the cyclooctane. And that's the one that I mentioned has a really weird domain. But there's actually not a lot of work done beyond that, because this thing is complicated enough. And the more carbons you add, the more complicated your molecule and your positions that you can get are going to get. So there's been some work done, and there's actually this super fancy paper where they first identified that the domain was a Klein bottle combined with a sphere. And it's a sampling paper on cyclooctane. And so that's the most, like, I'd say, relevant one that I know of. But other than that, not a lot's been done just because it is so weird and complicated.
Okay, cool. Any other questions?
I have a few. Well, first of all, do you have any idea of you said you want to look into applications of it later on. Do you have any idea how this could be applied?
Yeah. So what chemists have used previously are something called merge trees. So it just says, like, when those components merge, it really captures that, like, merging behavior that we talked about. But sublevel set persistence captures any dimensional critical point, not just when things merge. So chemists are interested in that just to figure out the underlying structure of the molecule itself. And if you're able to know this information about the molecule in general, so if we, let me back up a little bit. Let's find a good picture. Okay, so these, see the screen, there we go. So why the chemists in the first place care about these critical points and these, like, merge component things is because there are certain things called energy barriers, which says what is the energy it's going to take to get from this configuration to this configuration. And those are super important because when you're doing like chemical reactions, like, the amount of energy you have is going to determine what configurations you get along the way, which will help you model your scenario. But what can happen if you just consider them, like, the lowest minimum where these things combine, if you have maybe, here's your lowest energy barrier, here's your next lowest. In chemical reactions, right, if you have enough energy, you don't know which path it's going to take. So if you only account for this path existing, you have no idea that this one's going to actually come into play. So the more information you can capture about these molecules in general will give you more information about the chemical reaction, which chemists seem to be interested in, at least at first glance.
Cool. My other question is, like, nothing to do with topology actually, but all these different rotations and stuff, do like permutation groups ever come into play with just, like, there's so many rotations? Do they relate ever?
That is a really good question, and I don't know the answer.
Okay.
I feel like you're right, and it could.
It just seemed like it was that, like, you were just going in that direction with the more complicated molecules.
And that might be interesting to think about if, like, especially with the ones that have this super complicated domain, if you could at least say something about their structure, if you could model. I haven't thought about it. That's a cool question.
Cool. Well, thank you.
Okay.
All right, well, if there's no further questions, I'd like to thank Brittany again.